Right. Hello, everyone. Good morning. Trying to get my email set up so that in case we Zoom cuts out, you can send me an email that can join back. It's happened once or twice in the general chemistry classes. So, if there are any questions before we start, let me know. Okay. It's up and running. So no questions before we start?
Morning. I have one question about the homework we just submitted, homework number 7.
Yes.
My question is about question 2.2 and 2.3.
Okay.
And my specific question is, there's a formula we can use to find the boiling point, which is what I used, which is ln of Psat over Psat equals negative HVAP over R times 1 over T2 minus 1 over T1. And that's in a quantity. And so I solved for the boiling point using that, but then I also wanted to test out Antoine's, and using the Antoine's constants, I was able to get pretty much the same number. So is there a way that's more accurate?
You're talking about the way you solved in 2.1 you were given 4 different points.
Right.
And you were let's see if I think we have that from office hours.
Oh, then I can look at it in office hours. I don't want to waste your
But I
time.
mean, so the main thing is that if you're only given 2 points, then you could use the formula you mentioned to answer 2.1. But graphically, if you use all 4 points, then to calculate 2.2, you can either it ends up being the same thing. You can pick, because you have an average or an estimated delta H, including all 4 points. You can then calculate the delta A, the new boiling point, using the using the pressure at 1 bar.
Oh, I see. Okay.
And
Got
usually,
it.
so there's two aspects of this problem. One is interpolation, the other one is extrapolation. And so an interpolation is 2.2, where you have data that exceeds the 101 kilopascals point. So you should use the point closest to it, which would be, let's say, the 100 degrees Celsius point, to calculate the new boiling point. And then the extrapolation, if you have a point that's outside your data set, then you should again use the point in the data set that's closest to you. So if it's a high pressure, then you should use the highest pressure measured. If it's a low pressure or temperature, then you should use the lowest pressure or temperature measured.
Gotcha. Okay, that makes sense. Okay, thank you.
You're welcome. All right, any other questions? All right, well, we'll just continue. So, so I sent, so I've opened up my email. Like I said, this has happened a couple times. where Zoom cut out and I didn't know. And so if you shoot me an email, I can rejoin the meeting pretty quickly and avoid anything happening that's okay. So we're continuing with colligative properties. We've planned to finish that today. So this would be the boiling point, elevation, freezing point, depression, and osmosis. Now, those are the key. We also have vapor pressure depression. So we call Raoult's law, AOUL. So although Raoult's law isn't necessarily grouped in the same way as colligative properties, it is one. It's independent of the variable, at least ideally. And so depending on the mole fraction of the particular compound, we're saying that it's pressure. So when we do an example, we'll include Raoult's law in our colligative properties calculation. Okay, so this is an entropic driven problem, colligative properties, and we're going to use chemical potential to analyze it. In general chemistry, you're just usually given formulas for these, but our goal is to derive where it comes from, given our work in Unit 3. Okay, so the system we have looks like this. So we have a pure solution, pure substance with a P star, and then we have a solute plus solvent, and this is right, so this is the lowering of the temperature, freezing point, but you could also consider the boiling point elevation, because we have to increase the boiling point to get to the exact same balance of chemical potentials. All right, so how do we start the problem? Well, this problem is started by using, and this is when we introduced chemical potential back in Focus 4, we mentioned that this was going to be probably the most important expression of the chemical potential, which is that it has to be equal independent of phase. And that's really where its usefulness comes from, is where we use it over and over again, because at any interface, right, if it's a liquid gas interface here, because this is the same as, oh, I didn't put the, should be the liquid there, that the, so this is mu A liquid. So that this expression here is what is really powerful. This is the most powerful tool we've been using to analyze solutions, but also pure solvents, pure substances. When we looked at phase behavior, that and it doesn't matter its composition, doesn't matter the phase, that the chemical potential has to be equal if the system's at equilibrium at any interface. And now what we're going to do is, well, we're just going to write this term in terms of the pure substance and a factor, right? The factor, and we talked about the factor, derived it. So this is the factor that it's not a pure substance, and it is that allows us to connect. Okay, well, we'll just add on a factor or a term that takes us from, that allows us to look at the pure substance chemical potential plus some additional term, right? So that's our entrance, right? Our entrance into how solutes, because solutes are part of mole fractions, even though it's the mole fraction of A itself, this is the term that's going to allow us to include solutes as changing, right? As changing this particular dynamic that, and it's actually this one, right? The how this changes and what we can use to predict what terms it would most depends on. So that's our goal. Okay, so if we rearrange that equation, we only have pure. So this here is a focus for expression. This is only pure substance terms, and so if that's the case, then we can write what we did in focus 4, that the difference in chemical potentials is now equal to delta G of vaporization. And we're picking vaporization because of the phases involved of the liquid gas interface. And that the ln of XA equals delta G of vaporization over RT. All right, any questions so far before we continue? Okay, so then, so we don't stop here. This is a ln, sorry, ln. What we're going to do is we're going to take the, and it might seem like a strange thing to do, but we're going to do it. That first we're going to take the derivative of both sides with respect to temperature, and then we're going to integrate to get the total term again. So the reason is because we know something about this term here, and what we know about it, given what we did in focus 4, is that it leads to the delta H of vaporization that we're going to show. And that's what we really are going to want to have access to, is the delta H of vaporization, because this here is going to be temperature independent. More or less, right? The delta H of vaporization is temperature independent. Delta G of vaporization is temperature dependent, right? So we don't really want this term. We only want the temperature dependence to exist in explicit functions of temperature, not in delta G and temperature, at least in the final presentation of the formula we're going to derive. All right, so how do we get to the delta H of the vaporization? Well, let's take a look at what we did in focus 4, which is, well, what's this? So we'll just take R out of it because we're not really interested in R. And, well, this is going to be equal to D. This is a total derivative, right? And both delta G and T are functions of temperature. So that means we have to have a D delta G vaporization dt 1 over T plus delta G of vaporization of a minus 1 over T squared, right? So we get two terms, and this is really what we worked with in focus 4. And as we developed the Clausius approach, Clausius-Clapeyron approach, and here, right? So what's that? So let's take a look at dg. So dg is I always like to use this over and over because I don't like memorizing anything. So it's minus S dt and plus v dp. And so that means that the partial of g with respect to t is equal to minus s. And that's what we have here, right? So we only have a function, so it's a total derivative of t with delta g, but g's the only term in there, and then that's the same as this guy. And so what we have here is 1 over t times minus, well, minus s vaporization plus and so what do we do now? Well, what we're going to do now is, well, we're going to say, well, delta G of vaporization delta S or S vaporization. We'll put the delta S here. So ugly. So then delta H we'll just say we could just plug that in now. So we have delta G of vaporization, and I mean we could do two things. We could solve for delta S of vaporization and plug it into here, or we could take the delta H of vaporization and plug it into there, right? So it's either way, but either one, but either approach is going to include or incorporate delta H of vaporization into the equation. There's no really particular preference. It just, we could do either one. We could substitute in for delta S or substitute in for delta H. Are there any questions about that? You see how you could do both. You don't want to do both, but you could do either one of them. Okay, so let's do, well, we just plug in for how the equation is written. Okay, so if we redo that, then we say this term dt 1 over r of delta G of vaporization over T is equal to minus 1 over T delta S of vaporization plus delta H vaporization let's see, I got to get that other delta H of vaporization minus T delta S of vaporization, right? So that's the delta G of vaporization term times minus 1 over T squared, right? So that was the total term if we make that substitution. And then we get minus 1 over T delta S of vaporization. Then we get plus 1 over T delta S of vaporization, and minus delta H of vaporization over T squared. And we just, now all of this just equals delta H of vaporization over T squared. Don't forget our R. Now we just put R there. And this term, 1 over R dt of delta G vaporization over T. All of this was equal to, say, well, why did we do this? What was on the other side? The other side was d dt of the ln of xa. Right, so we've accomplished our goal. We now have our mole fraction. We're not completely in. We haven't completely connected the solute, right, which would be xb. That's what we want to do. We want to have what is the function of putting in different mole fractions of a solute into our temperature changes. So remember, this is what we're looking for. We're looking for how does the boiling point or freezing point change when we add some solute B to the solvent A. Solute B. Okay, so well, we could do a couple things here. First thing we should do is probably integrate both sides. Well, first of all, we multiply, so let's multiply dt to both sides. So we go minus delta H vaporization over RT squared. So we multiply both sides by dt and integrate from, we do T1. So usually what we do is we put T star here to some new T, right? So T star being the standard freezing point. And so here we're going to get minus delta H of vaporization. Vaporization over R. And we have a minus 1 over T evaluated at T star to T. And this equals ln of XA. Since we're taking the integral of something that had just a total derivative of it, gives us ln of XA. Okay, any questions so far? No questions? No emails? Okay, I'm assuming everybody is happy with what we're doing. So now we're going to work with this term. We have to put in the limits of the integration, and then we're going to take a look a little bit at that logarithm. All right. So the ln, I'll just rewrite that so that we can. Now it's a plus. Oh, all right, so we're going to do a couple things. Number one, we can put in T star minus T all over T star T. All right, so we just change the difference there to make it a common denominator and put it in a form that was very similar to what we saw before with our pure substance when we look at Clausius-Clapeyron. And then here, what we're going to do is we're going to go one ln. We're going to change to the solute. Okay. And now we're going to begin some approximations here. Okay, that you say, well, why? So what do we mean by that? So we're going to look at so XB. This is the solute. Is close to 0 when you compare it to XA, meaning XB is much less than 1. And so what's commonly done here is to expand the logarithm about So the logarithm, not just the logarithm, but about xb equals 0 using a series expansion. So you can kind of think of it as two different things, right? We're either expanding the about xb of 0, which would be a Maclaurin series, or we're expanding ln about 1, using the Taylor. So Maclaurin or Taylor. It's really, in a sense, very equivalent to us. It's just a matter of which term, how do you set the problem up? But in general, the main thing is we're using that xb is much, much less than 1. So let's take a look at that. So we have ln of 1 minus xb is approximately equal to what? Okay, well, it's approximately equal to, now this is f of x, so approximately equal to f of x evaluated at x equals 0 plus f prime of x evaluated at x equals 0 times x plus, and then higher order terms, right? That's what HOT is, higher order terms. Stands for hot. As in, and it's just a way to say terms that we're not interested in right now, right? So we're usually, when you look at Taylor series or Maclaurin series for these types of formulas, really only interested in the first two terms. But obviously, as we would like more significance or getting more accurate results, we might include a third term. But in terms of the derivation of this result, we're only going to use the first two terms. So we just use this formula for the first two terms. Then we say, okay, we got the ln of 1 minus xb evaluated, right? Evaluated at xb equals 0 plus, and now we have 1 minus xb, and so 1 minus xb is going to be the derivative of this is going to be 1 over 1 minus xb evaluated at xb equals 0. And this is all times 1 minus xb, right? Which would be the term that's, well, if we're taking the derivative of respect to xb, taking the derivative, we're taking the Maclaurin series, then it's just xb, right? So that's sort of the difference. You could do the Taylor series, you could do the Maclaurin series. So we're doing the xb equal to 0, and then so this term would be xb, right, minus xb. Okay, so those will be our two terms, and so let's flip the page now and say, well, what does that give us? Well, we get, well, this term here is going to be the ln of 1. So let me just erase our higher order terms part so we have the result.
I had a quick question.
Oh, yeah.
Why is it negative xb for the second term in the Maclaurin?
Because well, we're taking it with respect to, so it's what is present inside. So I mean, it's because it's not 1 plus xb. Right. So, well, okay, because there's two ways to think about it. Let's go this way. Maybe it's the more correct way to do it. The derivative of dxb of ln of 1 minus xb, maybe this is the problem, 1 minus xb, is 1 over 1 minus xb times minus 1. So either we put the minus 1 here because we're taking the derivative of xb, or we're taking the derivative of minus xb, right? And so it's just a matter of what we're doing. Because if we treat it as like minus xb, then the derivative is positive, but we have to put minus xb outside in the term we're taking the expansion of. So I think it just depends on, how about we just do this way? It's probably much more standard. So the derivative should have been minus 1, and then we put in xb here, and then we're actually doing everything in terms of xb instead of minus xb. So it just depends on which variable you're actually working with. But I think a much more standard way of doing the derivative is, let's take the positive version of xb, do the derivative of that, but that means we now have a minus 1 in the derivative.
Okay, I get it. Thank you.
Yeah, and thanks for pointing that out, because it's really about, I mean, that was a very subtle thing, and important though. Okay, so that means that we get the ln of 1 plus 1 over 1 plus 0 times minus 1 times xb. So doing all that work, what we can see is that the ln of 1 minus xb is approximately minus xb, right? So that's our result. And we're going to put that up here. Okay, so let's do that. So we get the ln of 1 minus xb is more or less minus xb, which is equal to delta H of vaporization over R, 1 over T star minus T over T star times T. And we're going to put the minus sign on the other side. Why? Because what we're going to do is we're going to say T minus T star that's times a minus 1, and then we get another minus 1 from this one. So the first, I'll put a 1 here. The first minus sign is from the sign of minus, is the sign of xb. And then the second minus sign, 2, is by reversing T and T star in the numerator here. And so what does that do? Well, that gives us xb is now delta H. The minus signs cancel, and we get delta T now, right? So delta T, and then since T star and T are usually fairly close, and we already have approximations, what's often put here is T star squared. So we have delta H of vaporization over R T star squared times delta T. And that's pretty close to how the final form of this equation works. So delta T now is equal to R T squared, T star squared over delta H of vaporization times XB, which is moles of solute, over total moles. But the total moles, again, we're still in our approximation phase. So we're just, the total moles is really is moles of solute plus moles of solvent, which is again just moles of solvent. So this pretty much is 0 moles of solute. Even though it's there, that's what's causing this effect, but we can approximate it as 0. And why would we do that? Because, well, we know that the moles of solvent is the mass of solvent. We could say kilograms of solvent over molar mass in kilograms. And so that's what we're going to do. We're going to change this to be moles. Oh, no. We don't want to have an equal sign here. But we're going to take, we're going to take this term, moles of solute over total moles, and what we want to have is moles of solute over kilograms of solvent times the molar mass. And what unit does that give us if we use moles of solute over kilograms of solvent? What's that unit called?
What is it,
Molality?
Yeah, molality, right. So that's the temperature independent concentration unit. So so let's make this a little bit nicer. So we're over here now. We have delta T is about, right? We're using a lot of approximations here, but it's about equal to R T star squared over the delta H of vaporization times the molality, and it's a little m, times the molality times the molecular mass. And we can do R T star molecular mass over delta H of vaporization times molality. And it's usually written as, you'll see it in books like italics and little, but it's little m, moles per kilogram. And there's no volume in there, so there's no temperature dependence on molality. That's why it's used. So RT star squared molar mass over delta H of vaporization is really ugly to write over and over again. So what you see here is a constant, and a new constant is given for freezing point and boiling point depression times m, and it comes, and so delta T of boiling is equal to KB m. Right, any questions about that? So we're not real, I mean, we have the exact same derivation for freezing point, so that's for boiling point. Freezing point, we're going to say same story, because it is. Right, same story, meaning the same derivation for the most part. And the effect of, so what does that mean? That means that delta T of freezing has to be about R T star, and this was boiling, right? So this is the boiling point T star of freezing or melting. Usually it's melting. Just put it's the same, but just how it's designated in books and things. Melting molar mass. So just keep in mind all the molar masses that you're going to do in the homework, and everything we do now is going to be kilograms, right? Anytime you have R in molar mass, you must be working in kilograms per mole. Over delta H fusion times molality, right? So exact more or less the same equation, and it's given. Now, one of the things that happens here is a minus sign is introduced.
Question.
Yes.
Is the TM star? Okay, there you go. Never mind.
Sorry, well, as soon as you said question, I looked at the equation and said, uh-oh, so I changed it.
Fair enough.
Yeah. Okay, so a negative sign is introduced because of the depression, meaning that T is less than T star. In the boiling point elevation, T is greater than T star. So to maintain the same sign, I don't know, well, just to maintain the sign convention for both of these, like the delta T, the change in freezing point, so a minus sign is introduced because that's how, because delta H of fusion is positive, molar mass is positive, T molar is positive. T molar, T melting is positive, and then you square it, and then R. And so there's no way to get a decreased value from delta T unless we put the minus sign. So that's what we do. All right, so let's do an example.
I have a quick question, Dr. Daly. For T star, that's the saturation for boiling and saturation temperature for melting?
Yes.
Okay, thank you.
Oh, wait. I'm sorry. I was just kind of going with your question. Saturation, what do you mean by that?
I know for like when we did Raoult's law, we defined the P sat as P star, the saturation pressure as P star. So I wasn't sure if you were applying the same thing for T.
Well, star for us means pure. So that means like if you were looking at, like we have a problem. So let's look at the problem. The problem is 4.5 grams of a substance dissolved in CCl4, 125 grams of it. So what we're saying is, when we say P star, we're saying that this is the vapor pressure of pure carbon tetrachloride. That's what we mean by star. Like T star boiling, well, this is going to be its pure boiling point. So that's what we mean by star. And so that's that's what we mean by star.
Oh, okay, that makes sense. Thank you.
Yeah, it's just because you're always going to have this information, pure melting point, right? You always have the pure, in any table, you're going to see, melting point of carbon tetrachloride. Boom, that's it. You're not given, melting point of carbon tetrachloride at 0.2 molal in, of HCl, right? So you say, what? That table doesn't exist, probably. So that's what these equations are designed for, is to say, well, let's estimate what that boiling point would be if we did have any substance. It doesn't have to be HCl. We have any substance. What would be the melting point now? Right? That's what we're trying to do. So this leads to an elevation of boiling point of 0.65 Kelvin. All right, so just that information. Oh, and then we have KB for CCl4 is 4.95 Kelvin kilograms per mole, and Kf of CCl4 is 30. Why are they so different? Why is Kf like 6 times greater than the boiling point term? Why do you think those constants are so different?
Is it because delta fusion is much greater than delta evaporation, evaporation, the energy required?
Yeah, well, it's just what you said, but keep in mind that it's 1 over delta H of vaporization and 1 over delta H of fusion. So it's not that, so delta H of fusion is usually much less than delta H of vaporization. And since since it's reciprocally related, then it's, because delta H of vaporization is always higher. To go from liquid to gas takes so much more energy than to go from solid to liquid. But you're absolutely correct.
Okay.
It is related to delta H though. All right, so, well, what do we want to know? We want to calculate delta TF, calculate the molar mass, and calculate the factor that the vapor pressure is lowered, right? So this is the Raoult's law. Factor, the factor vapor pressure is lowered. Okay, so what we have is that the molality is equal to delta T boil over KB. But this is also equal to minus delta TF over KF, right? So they're equal to, they're both equal to the molality. We haven't really calculated the molality. We can, but we don't. But the first question is to calculate delta T freezing. And so delta T of freezing would just be minus KF over KB delta T of boiling. And so delta T of freezing here would just be 30 over 4.95, which is about 6 times 0.6 Kelvin. So the freezing point depression should be about 6 times 0.6, 3.9 Kelvin. Any questions about that? Okay, so so we could have done the molar mass first because we have all the information from the boiling point, but we, just the way the question was asked, we calculated delta freezing point. So how do we calculate the molar mass? Well, we have the molality is delta T boiling over K boiling, which is 0.65 Kelvin over 4. We can use either value. It doesn't matter if we use the freezing point. So the unit, when you write it out, is molal. So 0.131 molal, and this unit is 0.131 moles per kilogram. So this is solvent here and solute. Woo. Sorry. Solute in the numerator, solvent in the denominator. So that means 0.131 molal equals moles of solute. So that's going to be mass of solute divided by molecular mass all over 0.125 kilograms of CCl4. So that was given in the problem that we had 125 grams of carbon tetrachloride. And so we only have one unknown, right? We could put massive solute in here, which was 4.5 grams. But we don't want that in grams though, right? We want that in oh, well, okay. It kind of does it. Okay, I left it in grams. Well, let's leave it in kilograms. Okay, sorry. Because it does these units actually are independent of each other. It looks like, oh, I got kilograms in the numerator, I better have kilograms in the denominator. It's not true, because the only thing, so this is 0.131. This is going to be moles per kilogram. So this kilogram down here is what needs to connect to that kilogram. The unit up here in the numerator is only going to define the mass unit for molecular mass. But I think good practice suggests that we should keep everything in the same unit. So let's do that. So that means that the molar mass is going to be equal to, well, let's keep it as a reciprocal for now. So 0.131 times 0.125. All divided by 4.5 times 10 to the minus 3 kilograms. So molecular mass is going to be the reciprocal of this. And I only did the reciprocal, which I got 275 times 10 to the minus 3 kilograms per mole, or 275 grams per mole. So we get the molar mass from this analysis. And again, this was a typical standard approach to determining molar masses before mass spectrometry was developed. Are there any questions about that?
I have a quick question. Is the molar mass that we're finding of the mixture or of the solvent?
No, just the solute, because remember in the numerator of our molality, this is all solute. The numerator is just the number of moles of the solute. So when we calculate the molecular mass, which is the denominator in our numerator, well, our numerator is a ratio of two values because it's the number of moles. When we pull that out, that's the molar mass of the solute, kilograms of solute. And it's only the solvent that's in the denominator.
Gotcha. Thank you.
You're welcome. Okay, so that's and then the last part, right? So we have our molar mass of 275. And the question is, using Raoult's law, how much, let's not start with that. So Raoult's law is saying, right, that the vapor pressure now is reduced because the mole fraction of the solvent is not 1, it's some other value. So let's take a look at that. So that would be P divided by P star is equal to X solvent, or 1 minus X solute. So we're looking at, well, what is this factor? How is the vapor pressure changed by the introduction of this solute? Well, so P over P star is 1 minus N solute over N solute and so this is 4.5 grams over 275 grams per mole over 4.5 grams over 275 grams per mole plus 125 grams over 152 grams per mole. Right, so and all of whoops. And with the 1 minus, right? So we plug this in and we get, it doesn't change by much, right? So so we have a 2% decrease, or the factor is 0.98, right? So the change in the factor would be 0.98, or 2% decrease. So that's how we would use this information to calculate molar mass, calculate other aspects, other colligative properties. Once you've analyzed one of the 3, you can then calculate the effect on the other 2 colligative properties. All right, any questions about that? Okay, so the last one, osmosis. Again, probably the one colligative property that is still an incredibly important laboratory value. I mean, boiling point depression and freezing, I mean, boiling point elevation and freezing point depression. I mean, this was really, really important in organic chemistry, probably up to about the 1950s or 60s, because there were no way to calculate molecular masses except through these colligative properties. And once mass spectrometry came in, it really took over that aspect of the analysis. But osmosis is still alive, and it's certainly extremely important. So let's take a look at it. We may not finish all of this today. We may, but we'll see. We may not get to any worked out problems, but we'll definitely pick it up if whatever we don't finish to Thursday, and then begin binary substances, or the foundations of distillation and separation. Okay, so what is osmosis? At least, what is the phenomenon? And here I'm going to torture everyone with some bad drawings, but just how it goes. I think it's important to get a visual here. So this is and you know, there's pistons in osmosis. Now, many of you who worked with osmotic pressure go, I didn't have any pistons, but so this here is a semi-permeable membrane. It's probably the only time in my life I've ever said semi-permeable membrane. And is in the context of osmosis. That's how you know you're dealing with osmosis, is because you're dealing with membranes that allow solvent to pass through, but solute does not. And then, in terms of equalizing the pressure, pressure exists because on one side of this, to resist solvent from crossing into the solute, because what's the tendency? The tendency is for the solvent to go in and dilute the solute plus solvent, and so the pressures are different. And this pressure that's different is the initial pressure plus some term. And this term is given the Greek equivalent of P for pressure, pi. And it's not lowercase pi, it's capital pi. So capital pi is used as this term of additional pressure that is necessary to prevent any of the solvent from going into the solute plus solvent. So that's one way to think of osmosis. Another way, a much more contemporary way of thinking of it, is an experiment where this is much more typical of what would happen in a laboratory. So here we have the solution of solvent plus solute, and then here we have you can imagine a dish here. Of pure solvent. So this distance here is caused by the osmotic pressure. So here's P pushing down. So osmotic pressure is going to be this difference, right? This difference in height between the solvent liquid height and the, because without this, remember, if we just had pure solutions in both of these, the pressures would be equal, right? So if this is open, and then they would equalize, but they're not equal. They're not equal because there's some additional pressure inside, right? This is due to this osmotic pressure. And that's the phenomenon that we're going to look at. And this osmotic pressure, pi, in this experiment, would be rho GH, right? We could relate it to, you know, and this is very common in manometers when you're looking at different pressures where one side's evacuated. And the old way they used to measure pressures would be through manometers, where looking at the difference in height of mercury in tubes or alcohol, where you could look at the different pressures exerted on a liquid through using this formula of rho GH. Okay, so that's the general problem. It's certainly not a complete introduction to osmosis, but it's the phenomenon, the laboratory phenomenon, where a pure solvent passing through it can be prevented, right? A solvent going through a semi-permeable membrane, going into a solution to dilute it, right? Dilute it can be prevented by the exertion of pressure, which is osmotic pressure. It's called the osmotic pressure. Okay, so how is it set up? Well, it's set up with chemical potential, right? This is our tool, and this is why it was so important. Because on both sides of this membrane, you have the same chemical potential. And so we have the pure liquid, and it's got to be equal to the solution. Right, so here we have the solution that has some mole fraction of a solvent, and here we have the pure. And that has to be true on both sides of that membrane. Right, so it's got to be true at both sides of the membrane. And another thing, so we're going to use that result, and so that means that mu liquid, so this is the pure standard pressure and temperature here, it's going to be equal to mu liquid of, now the P here, right, we have a new pressure. I don't know if let's go back here. This pressure is actually the star pressure, right? It's not P and the same P on the other side. It's actually a P star, but we know what P star is, so we're going to substitute. So this is P star, X, and then so we can say, well, that's going to be the same as P plus pi T plus, So let's just write it out here. So mu liquid 0 PT is going to be equal to mu liquid. So we're separating now because we know what X contributes to the chemical potential. We know what dissolving having the contribution of the solvent is. So we have P plus pi T plus RT ln of X solvent. And it's really important to keep in mind because there's two mole fractions, right? There's solvent and solute. So just to make it explicitly clear, we're looking at the solvent. All right, so the couple things though that, right, so let's look at the, so DG for the pure substance. And, well, no, sorry. Chemical potential, right, is DU for the mixture. This is a focus 5. And what we're gonna, so this is minus, well, let's just do it together. So we get DG is going to be VDP plus minus SDT. And so at constant temperature, DG is VDP, and it's equal to DU. So we have here DU is going to be equal to V. VDP. And so now we can say, well, this term, right, this term that we're looking at, mu liquid, is going to be equal to the integral of P to P plus pi. That's the change in pressure of Vm dP, which we could say Vm P plus, okay, well, we did of P evaluated going from P to P plus pi. So mu liquid is going to be Vm P plus pi minus P, or pi times Vm. So we have mu zero liquid Pt equals pi Vm plus RT ln of X whole. All right, any questions? Did that reverse? No questions? Okay, so then we have this term. Oops. And now what we can do is we can put in, so we have mu liquid and we have mu naught, and the difference between the two, right? The difference between the two is going to be equal to RT ln of X solvent. And all right, let's put that in. So we have, so what we're going to do is we're going to take this term and subtract them. So we have mu liquid of P 50 minus mu liquid. Right, so we'll subtract these two terms. So this is going to be, so we have mu liquid, mu zero liquid is going to be this term, and this term, so this term here, this P over V, this is du, right? So I'm going to have to put this as du, which is going to be also equal to mu right. So you have two terms. You have this one, and you have, so this is why there's a little bit of confusion here. So I'm going to change this a bit and say, here we have, whoops, we have u liquid minus mu zero equals pi v. That comes from this integration. And then we have up here, we have mu liquid minus mu L. So what I'm going to do is I'm going to change this because it's had some errors in our notation. So what we have is mu liquid minus mu liquid not. So both this equals pi v m. This is from the integration of VDM, the VDP. And this is also going to equal minus RT ln of X solvent. And this is from the top equation. So I lost my minus sign here, so that's why it looked like that substitution was wrong. So we would have this result equating the result from the integration, which is going to be here, and to the top term, which is the difference in the chemical potentials also. So we have two different chemical potentials, one relating the pressure to the mole fraction in the solvent. Apologize for that. Are there any questions about that?
So these are two separate changes of chemical potential expressions?
Exactly. So one is relating pressure, the other one is relating the related to the mole fraction. This term here, the RT times the mole fraction, ln of the mole fraction. That's right. Right. So then, so once we have that, this term PVM equals minus RT ln of X. X. So it's changed, right? It's changed to the minus the RT of the ln of 1 minus X of the solute. And we're going to make the exact same expansion, right? We're going to do the exact same expansion here that we did for the freezing point depression, because we have the ln, we have the ln of 1 minus something that's very small, X solute. So that means the ln of 1 minus X solute has to be about minus X solute. That's what we showed that you would get, right? If you look at the characteristic that X solute is much, much less than 1 by using the expansion about X solute very close to 0. So we get pi over Vm is minus RT X solute. Now it's a plus sign, right? Because we got a minus sign from here. So it's plus RT X solute. And so we're at the result, which is the moles of solvent in the denominator here, moles of solvent denominator over here. So we get pi V equals N solute RT. This is called the Van 't Hoff equation. And it looks like the ideal gas law. Well, we are not dealing with gases, right? We're dealing with solutions and its connection to pressures. It's a very interesting result coming from this analysis. And I'm sorry I had that extra term and had that change, but we changed it. It's the correct value. And so what we'll do on Thursday is we'll explore how this is used, how we can, looking at experimental data, extract the molar mass, right? Because that's what we're interested in, is how do we use this data to obtain molar masses of different substances. Okay, so with that, I will, are there any questions? We will stop here in terms of, so we'll look at experimental data, looking at osmotic pressure, and then move to the two-component vapor pressure curves.
When you went from X of solute to N solute over N solvent, is that just, are you finding the mole fraction of solute? Because then wouldn't it be N solute over N?
Yeah, you're
plus
absolutely,
N solvent?
yeah, you're absolutely right. This would be N solute over N solute plus N solvent. That would be X, right? X solute. But what we're saying is this is more or less, right? The N total is more or less N solute.
Oh, okay.
Yeah, so you're right. I did do that fairly quickly, but yeah, so that's the approximation, is that we say, okay, well, the N solute contributes very little to the sum. We can't obviously remove it from the numerator, but it contributes very little to the sum, and so we would put that as just N solute. Oh, wait, sorry, not that one. That's fine. The solvent is fine. It's the solute that contributes 0. So N total is just the solvent, right? That's what we'd expect to be, just in much greater amount of moles of solvent than solute. So N total would be that. So XS, the mole fraction of the solute, is more or less the N solute over N solvent. That's the result we used.
Okay, thank you.
Yeah, you're welcome. Thanks for pointing that out. I did that kind of quickly. All right, any other questions? All right, so again, more applications of the chemical potential. It just, in unit 5 is just, our focus 5 is just the application of chemical potential to all these systems. Then we'll continue it with equilibrium in focus 6. Okay, so with that, we'll say that class is finished. If you have any other questions, let me know. I'm going to change back to the Zoom room. If you have any questions, you can put it in the chat window or email me. We will continue with applications of osmosis and then the binary distillation curves on Thursday.
Thank you, Dr. Daly.
Yeah, you're welcome. Let's see. Let me go over here. Participants. Right. So, there's still manometers. Yeah, the old school. That's what people used to use. And when I was in school, undergraduate, they were still in the laboratories. You can believe it. They were there. Big tubes of mercury. I don't know what happened to them, but they used to be in the labs. All right. Anything else? All right. So nope, nothing else. Okay, everyone. Well, stay safe and see you on Thursday. We will continue and Thursday. So the homework 8 will include up to the end of lecture on Thursday, which will be both colligative properties and I'll post that right now after class. Okay, bye.